right, so these were the questions that were used on the AP exam this year for the people that took the test in person. So they actually took the tests in an actual, brick and mortar building, and these were the questions that they had. Most people say that these were a little bit easier than normal questions or from past years, but maybe the AP was just trying to go easy on people because of distance learning, who knows? All right, so our first question here. So the length of stay in a hospital after receiving a particular treatment is of interest to the patient, the hospital, and insurance providers. Of particular interest are unusually short or long lengths of stay. A random sample of 50 patients who received the treatment was selected, and the length of stay in number of days was recorded for each patient. The results are summarized in the following table and are shown in the dot plot. So we've got the table with 5 days stay, there were 4 people, 6 days stay, there were 13 people, all the way up to 21 days stay, there was 1 person. And then here it is as a dot plot, which dot plot is probably the more useful of the two here. Determine the 5-number summary of the distribution of length of stay. All right, so one thing you got to know is what the 5-number summary is. Well, it's the minimum, and then it's the first quartile, then it's the median, then it's the third quartile, and then it's the maximum. All right, it's basically the numbers that you're going to use if you were to make a box plot. Well, 2 of these are really easy to just read off. So the minimum is 5, the maximum is 21. All right, because minimum data value, maximum data value. The median, we need to find the middle one. We were told we had 50 patients. So one way to do that would be 50 plus 1 divided by 2 is 25.5. So the middle is going to be between 25 and 26. All right, so we can just count up data values here if we want till we get to 25 and 26. I have a feeling it's going to be in 7, but if we just start adding 4 plus 13 is a total of 17, plus 14 more is 31. We've already passed it, so the median's got to be somewhere in this bar here for 7. All right, now Q1. Well, if we take the bottom 25 and divide that in half, so like we had 25 in the bottom plus 1 divided by 2 because we want to find the median of the bottom, it's at 12.5. So if we just count up till we get to 12, so it'd be between 12 and 13, it'd be somewhere in here, which is 6. So Q1 is going to be 6. All right. Also, if we count down 12 from the top, we'll get to Q3. So that's kind of the tricky way to do it, but we could just count down 12 from the top. So 1 plus 1 is 2, plus 6 is 8, plus 11 is, I said 8, plus 11 is 19. So we've already hit it in there. So it looks like Q3 is going to be 8. So there is our 5-number summary. That's all they wanted. All right. If you want to add units like days, you can, but I don't think they even cared about that here. They just wanted the 5 numbers. Those are the 5 numbers. So 5, 6, 7, 8, and then 21. You do need to label them if they ask for them. All right. It's going to be annoying that I can't go back to numbers because I need Q1 and Q3 here and the median. Oh, well, we'll just remember what they are. Okay. Memorize them, guys. All right, so the next part here. So consider 2 rules for identifying outliers, method A and method B. Let method A represent the 1.5 IQR rule, and let method B represent the 2 standard deviations rule. Using method A, determine any data points that are potential outliers in the distribution for the length of stay. Justify your answer. All right, so the 1.5 IQR rule means that we need to find the IQR, which, if we remember right, is Q3 minus Q1. So that would have been 8 minus 6, which is 2. And then we take Q3 and we add 1.5 times the IQR. So that'd be 8 plus 1.5 times 2, which gives us, that's 3, that'd be 11. And for the low end outliers, Q1 minus 1.5 times the IQR is, so our Q1 was 6. So we're going to be 6 minus 1.5 times 2. So that's 3. 6 minus 3 is 3. All right. So anything above 11 or below 3 is a potential outlier. All right, so if we go back and look, I believe there was only one number that's beyond. Well, actually, there's two. We got one at 12 here and one at 21. So 12 and 21 are potential outliers. So 12 days and 21 days are potential or possible outliers. And there's none at the low end. Because the lowest we had was 5. All right, I don't know if we need to state that specifically or just say they had to be below 3 and we don't have any below 3. All right, the next way to do this is going 2 standard deviations in each direction. So the mean length of stay for a sample is, so that would be X bar because it's sample information, 7.42. The standard deviation, which we would say is S, is 2.37. Using method B, determine any data points that are potential outliers for the distribution using length of stay. Justify your answer. All right, so we would take our standard deviation, and I'm just assuming the 2 standard deviation rule means to add and subtract 2 standard deviations. And then we've got 7.42 minus 2 times 2.37. All right, now I'm gonna need a calculator, because those are not pretty numbers. There we go. I was wondering if it was gonna open on me. All right, so we've got 7.42 minus 2 times 2.37. And then we got the same thing with plus. Just gonna go back and change it to a plus sign. There we go. So we get 2.68. Oh, this is annoying. And yeah, there you go, 12.16. All right, so we had 12 and 21 last time. Well, 12 is not above 12.16. So the only potential outlier we have here is, well, so I'm just going to go ahead and write it out. So above 12.16 or below 2.68 are potential outliers. So only 21 days is above 12.16. So it is our only potential outlier. All right, so there we go, outliers. Hopefully we got those 2 parts. Neither one of those was particularly difficult. All right, and then part C comes in and then you're like, what are you talking about here, guys? This is just all sorts of weird. All right, so explain why method A might identify more data points as potential outliers than method B for a distribution that is skewed to the right, which is what we've got because we had those 2 points off to the top. So if we have a distribution that looks like that, why is method B going to give us more outliers? Well, for method A, we're kind of measuring from the median. Like we're doing Q1 and Q3 are about the median. But for method B, we're going from the mean, which is getting pulled up. Right? So that's really the only thing we know about skewed data is the mean is going to, or data that's skewed to the right, is the mean is going to be above the median. So let's just try and say something like this. So strongly skewed to the right pulls the mean to the greater values while the median stays in the middle. All right, so now why would that lead us to getting fewer outliers with B at the high end than we might with A? Well, if the mean's higher up, then if we go 2 standard deviations from it, we're going to go farther up than if we did if the mean was farther down. All right, so let's see. The IQR will also not be affected by skew, but standard deviation will. Standard deviation will be larger, leading to fewer outliers. Right, because we'll be going a longer distance up than if we do it like the 2 with this, and then 1.5 IQR with that was like there and there. All right, so that's kind of the idea. I'm probably not phrasing it great. You guys could probably phrase it better than I could here, but that's basically the gist of the idea, is that the means it's getting pulled up some because of the skew, and then it's also getting the data, the standard deviation is getting stretched out some because of the skew, which is leading to that second method getting fewer outliers than the first method. Or I guess I should say potential outliers than the first method. All right, so that's problem number 1. All right. Had 2 easy parts, then 1 kind of hard part at the end there. Problem 2 here. So researchers will conduct a year-long investigation of walking and cholesterol levels in adults. They will select a random sample of 100 adults from the target population to participate as subjects in the study. One aspect of the study is to record the number of miles each subject walks per day. The researchers are deciding whether to have subjects wear an activity tracker to record the data, or have subjects keep a daily journal of the miles they walk each day. Describe what bias could be introduced by keeping the daily journal instead of wearing the activity tracker. All right, well, if you're keeping the daily journal, then you've got to come up with the numbers somehow. And how are you coming up with the numbers? All right, so that means they could be responding with incorrect data, which is what we call response bias. All right. So without the tracker, people could be incorrectly measuring their miles walked per day. Possibly, I don't know, consistently overestimating would be something I might want to add. Possibly consistently overestimating their distance walked. All right, because otherwise, I mean, some of them overestimate, some of them underestimate, maybe it'll even out, who knows? But I think we're actually gonna, I think this would actually be linear regression with, miles walked, and the y-axis would be cholesterol level or change in cholesterol level or something like that. But yeah, that's what we want, is saying it's bias and that people could incorrectly measure their miles walked if they're not wearing the tracker. I mean, how else are you gonna measure your miles walked? Just guess. Well, I went out and walked for 20 minutes. That's probably a mile. Done. Yeah, you're much better off using a tracker. All right, part B. I gave you a long blank for part A, but you didn't really have to write that much, guys. All right. During the course of the study, the subjects will have their cholesterol levels measured each month by a doctor. The researchers will perform a significance test at the end of the study to determine whether the average cholesterol level for subjects who walk fewer miles each day is greater than those who walk more miles each day. Selecting a random sample creates a reasonable representative sample of the target population. Explain a benefit of using a representative sample from the population. All right, well, this is just kind of textbook definition. So if we use a randomly selected representative sample, then we can, well, then our results basically should hold for everybody in the population. So then we can maybe apply the results. Everyone in the population. And just to make sure I get the points here, I'm going to say, like, if we didn't use a representative sample, then we couldn't apply it. So if we did not use a representative sample, we could not apply it. Apply, I guess I should say the results, not it, to the population. All right, if you want, you could say more like if you just grabbed all men in your sample, then in your population was men and women, then your results would clearly not apply to the women because you only had men in your sample. That's what I'm trying to get at here, is you want your sample to be representative of everything in the population. And if it's not, then it doesn't apply to everything in the population. Oops. Next one, suppose researchers conducting the test or conduct the test and find a statistically significant result. Would it be valid to claim the increased walking causes a decrease in average cholesterol levels for adults, the target population? Explain your reasoning. All right, well, the key word here is, I did kind of emphasize it, causes. We can only infer a cause and effect relationship if we have an experiment where we randomly assigned the treatments. We didn't randomly assign them to walk. So we cannot infer a causal relationship between, I'm going to put my context in here, walking, I don't want to say distance or increase, I'll just say walking, and cholesterol levels. Because treatments, aka the distance walked, were not randomly assigned. In other words, it's not an experiment. It would be an observational study. All right, so I'm just adding those in there, so hopefully you guys can remember. So if we're just observing something, like we're watching to see how far they walk and what happens with their cholesterol level, that's an observational study. If we assign a certain group to walk, 3 miles a day, and we assign another group to not walk at all each day, then it would be an experiment. We don't really want to do an experiment like that, though. It's kind of rude to be like, you're not allowed to walk. You just stay on your couch all day. Some of you are like, sign me up. I understand, yeah. I will just stay in this chair all day. All right, on to number 3. So that one was kind of quick and easy, but that's your basic experiment design one. Usually they might add a little like, how do you choose a random sample? That would be another thing. Put everybody's name in a hat, pull them out, voila. There's your random sample. All right, number 3, to increase morale among employees, a company began a program in which one employee is randomly selected each week to receive a gift card. Ooh, gift cards, yeah. Each of the company's 200 employees, oh, there's 200? Oh, no, just one a week? That's not much. Is equally likely to be selected each week, and the same employee could be selected more than once. Oh, man. Each week's selection is independent from every other week. Okay, well, that's true because everybody's name's going back in, it sounds like. Consider the probability that a particular employee receives at least one gift card in a 52-week year. Define the random variable of interest and state how the random variable is distributed. So our random variable X is going to be the number of times an employee wins a gift card in 1 year. All right, or 52 weeks, yeah. All right, so X is the number of times an employee. So we're like picking an employee and we're saying, how many times did Fred win? Well, Fred won 0 times, or Fred won 5 times. Fred was really lucky. All right, and so we've defined the random variable of interest and state how that random variable is distributed. Well, we have n trials. We have 2 options. Each trial, they could win or not, more likely not. We have a fixed probability. The probability of someone winning is going to be 1 out of the 200 employees. And that's going to remain the same because they're independent. We were told they were independent. Now I did this all out of order, but here's our B, here's our I, here's our N fixed trials, and here's our same probability. It spells bins, you know, in a different order. All right, which tells us that this is going to be a binomial probability distribution. I mean, if this was me, I'd be taking out a person after they won, and that would kind of change it to geometric, but that would make it a lot more complicated and stuff like that. All right, so this is binomial. So we've defined our variable, and we've said that it's binomial. All right, next one, determine the probability that a particular employee receives at least 1 gift card in a 52-week year. Show your work. All right, at least 1. All right, we've done some at least problems before. It's been a long time, I know. Some of you longer than others. But when we do at least 1, well, that would be equal to, or, well, I could probably do this the other way around. Plus, I mean, the other option is if they win at least 1, so they win once or twice or 3 times or 4 times or 5 times or all the way up to all 52 times, I guess it's possible, plus the probability that they win 0 times is equal to 1, because those are the 2 things that can happen. They're complementary events. So the probability at least 1 then would be equal to 1 minus the probability that they win 0 times. All right, so that's going to be 1 minus the probability that they lose 52 times, which is 1 minus the probability that they lose on any given time to the 52nd. Now, the probability that they lose, so we said the probability that they win up above was 1 out of 200. So the probability that they lose is 1 minus 1 out of 200. Or it's just the other 199 people that don't win every time. So that's the probability that goes there. So we get 1 minus 199 out of 200, 52 times. So they're going to lose all 52 times. All right, and now we go to our trusty calculating device. All right, so we get 1 minus 199 out of 200 tries, and we're doing this 52 times. What's the probability of losing 52 times? Then 1 minus that gives us 0.229. All right, so we get 0.229. There's our answer. Done. Checking the attendance. We got people coming and leaving here all over the place. All right, but there's our answer to that one. That's it. So it's just 1 minus the probability that they lose 52 times is the probability that they win at least once. Complementary probabilities. All right, moving forward. Calculate and interpret the expected value for the number of gift cards a particular employee will receive in a 52-week year. Show your work. All right, well, the expected value for binomial is just n times p. N is 52, p is 1 over 200. So we get 52 out of 200. I probably want this as a decimal. It looks like it's 0.24 or something like that, or 0.26. I think it's 0.26. Let's just type it in. 52 divided by 200. Yeah, that's 0.26. Yeah, there it is. And we probably want some units here. So 0.26 times they win, or gift cards won. So for each individual employee, their probability of winning is 0.26, or they're going to win on average 0.26 gift cards. And it says and interpret. So we did the calculating part. Now we want to do the interpret part. So this would be on average, because this is an expected value. And I mean, it's not possible to win 0.26 gift cards, is it? So this is what happens on average. I don't want to say we, because we're not employees there. Employees can expect to win 0.26 gift cards per 52 weeks. I guess I don't need a dash, but they were saying 52-week year, but for 52 weeks. There we go. All right, so there's B. So there's our and interpret. So always look out for that, guys, because a lot of times they won't just ask you to calculate. They'll say calculate and interpret. So do the calculations, get your points there, and then write the sentence to get your interpret. If they don't say interpret, then you don't have to. All right, part C. Suppose that Agatha, an employee of the company, never receives a gift card for the entire 52-week year. All right, well, based on her experience, does Agatha have a strong argument that the selection process was not truly random? Explain your answer. All right, so if she didn't win, that means she's going to lose 52 times, all right, which we've already calculated. All right, we've done the other way. It's 1 minus the points. Was it 229 is what we got when we did that? Nope, didn't go far enough. There we go. Yeah, there it is, 0.229. All right, so let's see, 1 minus that would give us 1 minus 0.229. Oh, it doesn't like it when I type two numbers twice. There we go, 771. So the probability of this happening is 0.771. That's not exactly a small probability. All right, so based on your experience, does Agatha have a strong argument that the selection process was not truly random? Explain your answer. No. There is a 0.771 probability. Probability that she will not win in 52 weeks. Which is more than half. All right, it's a high probability. All right, so we do want to say something about that being a high probability. All right, usually we compare things to 5%. That's definitely way more than 5%. Like if we were doing a hypothesis test, we'd be like 0.771 is definitely greater than 0.05. So, you know, we're going to reject that hypothesis, or we're not going to reject that hypothesis. All right, next up. So that was that one. On to number 4 here. So the manager of a large company that sells pet supplies online wants to increase sales by encouraging repeat purchases. The manager believes that if past customers are offered $10 off their next purchase, more than 40% of them will place an order. To investigate the belief, 90 customers who placed an order in the past year are selected at random. There we go, there's our random. Each of these selected customers is sent an email with a coupon for $10 off the next purchase. If the order is placed within 30 days, of those who receive a coupon, 38 place an order. Is there convincing statistical evidence that the significance level of alpha equals 0.05, that the manager's belief is correct? Complete the appropriate inference procedure to support your answer. Here's our significance test. That was not straight. Oh well. All right, so it looks like we are dealing with, so we've got percents here. We got 90 customers, 38 out of the 90. So we're taking one sample. So this is a one sample. Looks like we're working with proportions. So we're going to do a Z test for P, where P is the true proportion of customers who place an order after getting a coupon. Place an order within 30, and didn't look too well, days of getting a coupon. I don't know if you need to write all that. You probably don't, but just customers who place an order would probably be plenty. Our null hypothesis is going to be that P is the 40% that we thought it was. And our alternative is that it's going to be more than 40%. And let's see, our alpha value here is 0.05. They gave that to us. Our P hat value is 38 out of 90. So that means 90 is our N. All right, so now we're going to check our conditions for the one sample Z test for P. Remember Zaptax, if we're using P, we're using Z's. So first condition was, did we have a random sample? We certainly do. Random sample is stated. Check. All right, you guys probably aren't going to be able to put check marks on yours, so just make sure you save random sample was stated. That's plenty. For the normal condition, so we want N times P, P naught, these guys. This is the P that we use. So we use 90 times 0.40 and 90 times 1 minus 0.40. So that's what, 36? And this would then be 54. Both of those are greater than or equal to 10. Both of those check out. So that means we have an, I should say approximately. We have an approximately normal sampling distribution. All right, so now that we're on the AP exam, don't forget to add in the approximately. All right, and then the last one, independence. So our N equals 90. Surely that's less than 10% of all customers. So as long as there are more than 900 customers, we should be fine. Hopefully there are more than 900 customers to this store all time or in the last 30 days. All right, now we're going to actually do the test. So it's a one prop Z test on our calculator. So we don't need to show work. We can just do it right on our calculator. All right, so let's see. Stat test. One prop Z test, number 5. Let's see, our P naught was 40%, so 0.40. We had 38 out of 90 people come back and use their coupon. And we want to know, was it greater than? Well, it's already set for greater than, cool. And calculate. So let's see, our Z is 0.43, our P value is 0.33. We've already got the P hat written up here, and then we've already got N written up here. So 0.43 for Z. We do want to write that down. And our P value, notice I don't write P, I write P value is 0.33. I don't want to confuse that with some other things. All right, and now that we've got our P, we write our conclusion. Now, if we were working with mean, we would write down degrees of freedom, but we don't really have degrees of freedom here since we're working with z's and not t's. So we're going to say since our p-value is 0.33, that's much greater than alpha, which is 5%. So p is not low, so we're going to fail to reject the hoe. And our hoe was that p equaled 0.40. So that means we don't have evidence for the alternative hypothesis. So we do not have significant evidence that more than 40% of all customers will, let's see, what will they do? Place an order. Place another order. Given a coupon or something like that. I don't know. Place another order is probably fine. Or that the true proportion of blah, 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 blah is greater than 40. You could also say that. All right. Notice I did say all customers in there. That gets me my population stuff. Inferences about population. So we got to make sure it's population, all customers. Or you can say that we do not have significant evidence that the true proportion of customers who placed an order within 30 days of getting a coupon is greater than 40%. You can also say that. That is 100% correct just as well. All right, so there's number 4. That was our inference problem on this test. All right, pretty much all of them used to have an inference problem. Oh, and there's a part B. Okay, let's clear that out of the way. So let's see what they're going to ask. Based on the conclusion from part A, all right, which of the 2 error types, type 1 or type 2, could have been made? Interpret the consequences of the error in context. All right, so type 1, let's see if I can remember which one's which here. So type 1, the hoe was true, and then the error was rejecting the hoe. Now, we didn't reject the hoe, did we? So it's not a type 1. It's got to be type 2. The ha is true, and then the error is failed to reject the hoe. Now, this is what we did. So it is possible, I mean, it's not any fault of our own. It would just be bad data, an unlucky sample, but it is possible we made a type 2 error. All right, so now I've answered the first question. Based on the conclusion of part A, which of the 2 error types could have been made? Type 2. Interpret the consequence of the type 2 error. All right, so we believe, I like my other writing the other way better. We believe that P is not significantly different no, not different. Greater than is what we want. Greater than 40% when it actually is greater. So more customers would place a new order with a coupon but we conclude it's still only 40%. I mean, maybe that would lead us to send out more coupons, but or maybe we should think we should send out more coupons, but we didn't send out more coupons because only 40% were using them. I don't know, but that's it in context. So we've got our coupons. We've got basically what they want. I think is this sentence right here. All right, but we do need something about customers and coupons and orders. So I added this another sentence just to make context in there. So we believe that the proportion that will make a return order or make another order is not significantly greater than 40% when it is actually the customers is actually. So we do need context in there. So that's why I added this second sentence, because I realized my first sentence didn't really have much context. All right, so don't forget context. That's important on these questions. All right, on to number 5. This looks like our probability one here. Probability from a chart. So a research center conducted a national survey about teenage behavior. Teens were asked whether they had consumed a soft drink in the past week. The following table shows the counts for 3 independent random samples from major cities. Well, of course, they're independent. They're from different cities. That makes sense. Suppose one teen is randomly selected from each city's sample. A researcher claims that the likelihood of selecting a teen from Baltimore who consumed a soft drink in the past week is less than the likelihood of selecting a teen from either one of the other cities who consumed a soft drink in the past week, because Baltimore has the least number of teens who consume soft drinks. Is the researcher's claim correct? Explain your answer. So let's say this, they had 700, they had 1,200, they had 1,400. So, I mean, they do have the least number, but they're claiming that the likelihood of selecting one is less. Well, that's probability. So from Baltimore, the probability that we get someone that consumed a soft drink or soda or whatever, given that they're from Baltimore, is 727 out of 904. All right, we want to compare that to the other 2 cities. So the probability that they compared or had a soft drink, I did that the other way around, didn't I? There we go. Given that they're from Detroit, would be 1,232 out of 1,663. And then the probability that they got a soft drink in the last week, given that they're from San Diego, would be 1,482 out of 2,280. So these numbers are higher here, but if I'm also noticing that the populations or their sample sizes were also higher. So let's throw these in the calculator and see what we get for each one of those. So let's see, we've got, oh, we gotta get out of that. So 727 out of 904. There's our first one, 80% it looks like. 1,232 out of 663. There's our next one, 74. Well, that one's already lower. We can probably stop and say, nope, they're wrong based on that. And the other one is 1,482 out of 2,280. I added an extra number in there, didn't I? Second entry, nope. Second entry, there we go. There's that extra 2 in there somehow. 65. There we go. So there's our 3 answers. So this one is 0.804. This one is 0.74. I guess that would round to 1. And this one is 0.65. So on the contrary, they are actually wrong. They say that the least probability is Baltimore. Baltimore actually has the highest probability. So is the researcher correct? They are incorrect. The likelihood of someone having a soft drink in Baltimore is 0.804, which is greater than both Detroit and San Diego. How many of you guys have had a soft drink in the last week? I have not, but I would imagine a lot of you probably have. All right, so there's all that. Whew, that was a lot of work. Well, it wasn't really a lot of work, just a lot of explaining, I guess. All right. continuing on. So 80%, 74%. Construct a segmented bar chart of relative frequencies based on the information in the table. All right, well, we pretty much already did all the information, all the work we needed. Baltimore was at what, 80%, I guess. All right, I'm just gonna, color it in or something. I don't know. And this was 0.80, was it 4? What did we get? I don't remember. 804, okay. Probably 0.80 is plenty. And then for Detroit, it was 0.74. And then the San Diego was 0.65. So 65 would be right there. 74 would be maybe up there. And I'm going to shade it in. And I'm going to make sure I'm going to have everything labeled here so that this is just in case they can't read it. There it is labeled. And this would be, was it none was the other thing? There we go. Just making sure I've got everything labeled they want. Which city had the smallest proportion of teens who consumed soft drinks in the previous week? Determine the value of the proportion. Well, it looks like it was San Diego. And that proportion is 0.65. All right, we've done the work already. We can write the work again if we wanted to, but we've done it already. So we don't have to write it twice. Consider the inference procedure. Ooh, this is different. Consider the inference procedure that is appropriate for investigating whether there is a difference among the 3 cities in the proportion of all teens who consumed a soft drink in the past week. Identify the appropriate inference procedure. Well, we would have 3 different proportions. So we can't do like a 2 proportion or 1 proportion test. 3 proportions puts us into the chi-squared territory. So this is going to be a chi-squared test. And then we ask, how many samples are there? Well, there were 3 samples. All right, well, 3 samples. If we have multiple samples and we want to see if those samples are the sameness. Test for homogeneity. So this is the chi-squared test for homogeneity. All right, and this is actually historic because this is the first time a chi-squared test for homogeneity has appeared on the free response ever. The other chi-squared tests have shown up before. Homogeneity has not, but this is it right here, first time. Identify the hypothesis for this test. All right, so remember the hypothesis for chi-squared was ho, no, and ha, an. So, or a. So ho, no would mean there is no difference in proportion who had a soft drink in each city. So ho, no. And then ha is just, we changed the word no to a. There is a difference in proportion who had a soft drink in each city. Voila, done. Ho, no difference in the proportions. Ha, there is a difference in the proportions. Done. And we want to make sure we have context, so we put soft drink in each city. I don't remember if it was last week or whatever, but there we go. Done. And then we're on to question 6. So question 6 is usually harder and longer than the other ones, and it counts for more points. For you guys, it'll be question 4. It is also supposed to be harder and longer, and it counts for more points. So make sure you try and do a good job on question 6. The general consensus is that they got an easy question 6 this year. So maybe you guys will get an easy one too. I don't know, we'll hope. So attendance at games for a certain baseball team is being investigated by the team owner. The following box plot summarizes the attendance measured as average number of attendees per game for 47 years of the team's existence. The box plots include 30 years of games played at the old stadium and 17 played at the new stadium. Old stadium, new stadium. compare the distributions of average attendance between the old and new stadium. Well, if we're told to compare distributions, we want to cuss and we want to compare it. We use comparison words when we cuss. So first, C. Don't forget to be specific. The centers. So this one looks to be about 16. This one looks to be, I don't know, maybe 25. So we want to say the new stadium has a higher average attendance than the old stadium, or median attendance. So the new stadium has a higher median average. And it's kind of weird because they're doing the average attendance and this is the median of the averages. Median average attendance. And their average was 25,000. Than the old stadium, which was about 16,000. All right, unusual, nothing unusual. So nothing, no outliers for either. So nothing unusual. All right, shape. This one looks approximately symmetric. This one looks a little bit skewed towards the lower numbers. So the old is approximately symmetric. New is skewed towards the lower numbers. I don't necessarily, I guess you could turn your head this way and say skewed right, or you can turn your head that way and say skewed left. So I don't necessarily want to say left or right. I want to say skewed towards the lower numbers because we have a longer section here and a longer section here than we did here and here. And finally, spread, which I don't know if I have room for down there. I'm going to put it up here, spread. All right, so this one has an IQR from there to about there. This one has an IQR. Is it okay if we skip the shape? I think it is okay. You're supposed to not have to do shape on box plot. So this one has an IQR of about 4. This one has an IQR, looks like maybe a little bit less than 4. So I think it'd be okay to say they're almost the same, or to say that the new stadium has a slightly larger IQR than the old. Has a slightly larger IQR than the old stadium. All right, you also could have compared range. Looks like that goes from 20 to, I don't know, maybe 11. And this one goes from 16 to 27. And so this is 11 and this is less than that. So you could have also compared range and that would be fine too. If you said the IQRs were approximately the same, I think that would still be fine, even if you did that, I think, because they're close to each other. So I just said slightly larger. All right, so there's our cuss and BS. There's our comparison. You guys will likely have a comparison of graphs on your test. It's an easy thing for them to ask. You don't have to write any sort of fancy symbols or anything. All right, so I can see that happening. The following shows an average attendance scatter plot. So let's see, we got the old stadium are the little boxes. The new stadium are the dots. Definitely a clear pattern in the dots, and the old one, well, kind of scattered there. Compare the trends in average attendance over time between the old and new stadium. So this is years across the bottom. So at the new stadium, we definitely have, like, here's the new stadium. Definitely a nice, solid, I would say, linear relationship happening there. All right, the old stadium, they seem to be fairly scattered. So looks like I want to say, and this is trends and scatter plots. So remember, we're going to do DUFs, direction, unusual form, and strength. So for the new stadium, there is a strong, positive, linear, so there's my direction, positive, form, strong, or sorry, form, linear, strength, strong. There we go. The strong, positive, linear relationship between year and attendance. The old stadium does not appear to have a linear relationship. Or has a very weak relationship. All right. So I think I've got it there because we've got the duffs. We don't need to say anything unusual. I mean, there's no outliers for either. If you want to put that, I think that's probably a good idea, saying that there's no outliers, so we get the unusual covered. But otherwise, I mean, you've got the trend here is that it's a strong positive linear for the new stadium, and the old stadium doesn't seem to have a linear trend. There doesn't seem to be any sort of slope happening there. All right, so there's B. Give you tons of room. You really don't need it. It's a pretty common trend here. Consider the following scatter plots. So number of games won, average attendance. Well, that looks like a pretty clear line to me. Very strong. And now here's based on the old stadium and the new stadium. So it turns out, looks like with the old stadium, they just weren't winning a lot of games. In the new stadium, they now are winning a lot more games. So whether they're winning more games, they're getting more attendance. So maybe that's what it was that was causing it, and not necessarily the year or the new stadium versus the old stadium. So graph 1 shows the average attendance versus number of games won each year, right? Describe the relationship between the variables. All right, I just missed that one. There we go. But there's definitely a strong positive linear relationship between games won and, I guess I should say, average attendance and not just attendance, with no outliers. All right, these are definitely all pretty darn close, lined up. I know I just missed that one when I made my circle there, but they're definitely good. I mean, we have one there and one there, but it's not far away. We'd have to have like a point over here to be an outlier, and we don't have anything like that. So we're really good, looks like, for that. Graph 2 shows the same information as graph 1, but also indicates the old and new stadiums. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Explain your reasoning. All right, so the rate at which they change, that's the slope. So here's about the line for these guys, and here's about the line for those guys. And it's basically saying, do these two have the same slope? It looks to me like they probably have a pretty darn close slope. So I would say it looks like, based on this graph, they have pretty much the same slope regardless of which stadium they're in. So the stadium doesn't seem to be making the difference. It's the wins that are making the difference. So let's see. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? No. The slopes of the lines for both the new and old stadiums appear to be the same. There's my reasoning. The slopes are the same, so doesn't look like there's any difference. All right, part D. I think this is it, isn't it? Consider the three variables: number of games won, the year, and the stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between the average attendance and the other variables. All right, so the two variables that go together are the number of games won and, well, what was the other one that we were looking at? Average, weren't we? Number of games won, average attendance, number of games won, average attendance. I guess old and new stadium would be year. So old stadium would be the old years, new stadium would be the new years. Okay. Where am I? There we go. Year stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between the average attendance and the other variable. So we want one of the variables that could affect both of the other variables. So let's see, number of games won and stadium, those could be related. Number of games won in year, well, it looked like they ended up being related. Year and stadium are definitely related. I would say year is the confounding variable here between the other two variables. But I'm going to check and see what somebody else said on this one just to make sure. So I do have an answer key that somebody else made. Unless you guys have thoughts on the topic. I haven't looked at it really. So I wanted to try and do this one completely. Stadium could be the confounding variable in the relationship between games won as the explanatory variable and average attendance as the response variable. Yeah, that's what we wanted with those two together, but where are we getting average attendance here? Oh, average attendance. Okay, there we go. Oh, okay. So I was getting confused because I wasn't reading on. I was just saying, how are these three variables? And it's between that and average attendance and the other variables. There we go. Okay. All right. So the stadium could be the confounding variable. Between games won and average attendance. So it's basically saying which one of these could be the confounding variable. And then why? Let's see. Well, how could the stadium affect the games won? And then how could the stadium affect the attendance? Right? Well, it looked like the new stadium was causing the attendance. And it looked like the games won maybe changed also based on the stadium. Right? So there appears to be a strong positive correlation between average attendance and games won, but average attendance all increased when there was, let me just bring this over and you guys can just read it from here. So based on graph one, there appears to be a strong positive correlation between average attendance and games won. Yeah, we definitely saw that. But average attendance all increased once there was a switch to a new stadium, as seen in graph two. That doesn't really, not a good sentence there, person who wrote this. Therefore, it is unclear what may have caused an increase in attendance. It either could be the increase. They didn't write in sentences. It's kind of annoying here. But basically what they're saying is that, well, right when they switched to stadiums, it looks like they also started to win more. So did that cause them to have higher average attendance, or did the new stadium cause them to have higher attendance? So did the games won change based because of the stadium and the attendance change because of the stadium? I think that's what they're going for there. I don't think they explain that well. All right. But let me take a shot at explaining it. So stadium could affect games won, and stadium could affect attendance. So stadium is a confounding variable. There, voila. And was that it? Stop, end of the exam. Okay, I will stop.